All right. So once we have figured out the idea behind how do we identify the oxidation states, the next thing that we need to do is we need to use the oxidation states and something called the half reactions to be able to balance the overall redox reaction. So here is an example of a redox reaction. I've got some MnO2 plus 4 HCl yields MnCl2 and Cl2 and 2 waters. Okay, so first thing that we have to be able to do is identify, well, what is being oxidized and what is being reduced. And I know it's already labeled here, but we need to be able to identify what's really going on here. So I want you to pay attention to what's really going on here too. So in this, with the oxidation states already labeled for you, can you see that the Mn in MnO2 is changing oxidation states from +4 to +2? Okay, so what that means, for that to do that, what that means is electrons have to be being gained. For it to change from +4 to +2, the +4 has to add 2 negative electrons to become +2. Okay, and so what we really have is, this is an ionic compound, and what we really have is an Mn2 plus here. So if that is the case, if it's going from +4 to +2, we can say that this is the half reaction that is being reduced. You're going to have one half reaction that is reduced, and you're going to have another half reaction that is being oxidized. And so I'm going to write down the half reaction that is being reduced. And I have MnO2 is being reduced to Mn with a 2 or a +2 oxidation state, excuse me. Okay, +2. Okay, so what I have to be able to do is recognize that inside the Mn and the O2 is the +4 oxidation state and the -2 oxidation state. And so that's cool, but that's what I have right now. Okay, so that is actually being reduced because +4 changes to +2. That must mean that +4 is having 2 electrons gained. 2 electrons are being gained there. Okay, so now we have to be able to take a look at, okay, well, what is being oxidized then? If that's being reduced, what is being oxidized? And so I'm going to look for a place where the oxidation state of one of the species is actually increasing. In other words, it goes from, say, a 0 to a +1 or a +1 to a +2, something where the oxidation state is increasing. Because if you think about it, the oxidation state increases when electrons are lost. And remember, loss of electrons is oxidation. So if I go look at the H's, H changes from +1 to +1. H doesn't change at all. So H is not actually going to be part of what is oxidized. But let me go look at chlorine. In the case of chlorine, chlorine changes from -1. That one is -1. We're not going to worry about that. But oh, look at that. Its oxidation state in that case, in the formation of the Cl2, actually changes to 0. So that means that my chlorine ion, Cl1-, is actually being oxidized to form chlorine 2. Okay, so those are my 2 parts. Did you notice me kind of ignoring the oxygen and ignoring the hydrogen here? And the reason why is because those are not changing oxidation states. The oxygen, oxidation state is -2, oxidation state is -2, nothing changes. I'm ignoring those. I'm really only paying attention to the ones that are changing. Okay, so now that I've got what is reduced, and let's go ahead and label this. So this is the reduction half reaction. And this one down here is the oxidizing or oxidation half reaction. Okay. So the first thing we have to do, we've done step number 1. We have written the half reactions, and that's going to be part of the struggle, is identifying which one is the oxidation, which one is the reduction. Now, something to keep in mind is that whatever you say is being oxidized is causing the reduction. It is the reducing agent. So whatever is oxidized, the thing that is oxidized is the reducing agent. Okay, and vice versa. Whatever is reduced is the oxidizing agent. It is causing oxidizing to occur. Okay, so let's say it again. The thing that is oxidized is acting as the reducing agent, and the thing that is reduced is acting as the oxidizing agent. Okay, so now we're going to go ahead and do step 2. And step 2 is balancing the atoms which change oxidation number. Okay, in the first one, in the reduction half reaction, the manganese was the thing that changed oxidation number, right? It goes from +4 to +2. And I just need to balance it by checking, do I have 1 Mn on either side? And I actually do have 1 Mn on either side. So then I go down to my oxidation half reaction. And in my oxidation half reaction, I have a Cl1 minus on the reactant side, but I have a Cl2 on the product side. So I am going to need to balance the atoms that change. So that means I need 2 Cl1 minuses. That balances out my Cl. So I've got that. Now I am going to add back in oxygens, enough oxygens, so that the oxygens on either side balance. And to do that, I'm going to add in some water. So do you all notice that the oxygen has a 2 right here on the left, but there's no oxygen on the right? So I'm going to go ahead and add in 2 water molecules. And what that does is that balances our oxygen. So now I have 2 oxygens on either side. Please do not let it bother you that right now that means we've got a hydrogen problem, because that's actually our very next step. If I do that same thing on the bottom, you'll notice I have no oxygens on either side, so I have no need of adding any extra water to balance oxygens because I do not have any oxygens. So I can go ahead and check this one off of our list here. Our next reaction, or our next part we need to do, is we need to balance our hydrogens. And balancing our hydrogens means that we need to make sure that we have the same number of hydrogens on either side. So on the right-hand side, I have 4 hydrogens, right? 2 times 2 equals 4. And so I'm going to need to add in 4 hydrogens on the reactant side so that I balance 4 hydrogens on the left, 4 hydrogens on the right. Okay, on the reaction on the bottom, there are no hydrogens, so I do not need to balance hydrogens. Okay, number 5, balance electrical charges with electrons. Okay, so this part is always going to be, it's going to follow a pattern, and you are looking for electrical charges that do not balance. And in this case, in the reduction half reaction, I have a +4 on the reactant side, but I only have a +2 on the product side. So that means that I need a new color. So let me grab a new color. We'll take that one. And I'm going to go ahead and add in, oh, that's the same color as before. Let me change. I'm going to go ahead and add in electrons so that I end up with a +2 on either side. And the only thing I'm allowed to do is add electrons. So if I'm adding electrons, please remember that electrons are -1. And if I add 2 electrons, that means I have -2 overall, plus 4 times 1 plus, which means I have -2 plus 4. That gives me +2 and +2, and so that's balanced now. Now I need to go down and balance my 2 -1s I have on the reactant side by adding in 2 electrons on the product side. So that means I have balanced my charges with electrons. All right. Number 6, if my number of electrons on the reactant and the product side, and that's from the reduction half reaction as compared to the oxidation half reaction, if my numbers of electrons do not match, I'm going to have to use coefficients as multipliers to get my electrons to balance. Okay, so right now I don't have to worry about that because my electrons are the same number, so I'm good to go. And now I get to do my favorite thing of all, which is canceling equal but opposite species. Remember in net ionic equations where we got to cancel out spectator ions because they were the same on both sides of the reaction? Well, now we get to do that again because they're the same on both sides of reaction. So I'm going to change one more time. I'm going to change my color. So here we go. First thing I get to cancel out is I get to cancel out the 2 electrons. Those are the same on both sides. Then I'm looking and I don't have any H's and I don't have any MN's and I don't have any waters. So everything else is part of the reaction. So if you don't mind, I'm going to clear the screen right now so that I have room to write because I have suddenly run out of room to write. So let me do that. Okay, so what I end up with is I end up with 4 hydrogen ions plus MnO2 plus 2Cl minus 1, and that's my reactants. On my product side, I end up with an Mn plus 2 plus 2 waters. And so that ends up being my entire equation. It's a net ionic equation, but it's an entire balanced redox reaction. Let's just check and make sure that it's balanced. Okay. First thing we check, there's 1 Mn on either side. Second, there are 2 oxygens on either side, and there are 4 hydrogens on either side. So our elements all balance. Next thing we're checking is our charges. I have a plus 4 minus 2, so I have a plus 2 charge on the reactant, and I have a plus 2 charge on the product. So now I have an overall balanced redox reaction. And we are going to stop right there and let you practice balancing redox reactions at this time.